Alright, today we're going to be talking about ROP chaining, our next chapter in smashing the stack. So at this point we've learned all about naive buffer overflows that assume no protections, right? So all you have to do in this situation is write whatever malicious shellcode you want onto the stack, then overwrite the return address to jump to the start of your shellcode. And there you go, we've achieved arbitrary code execution. Nice and simple. Unfortunately, there is an equally simple solution to this called DEP, or Data Execution Prevention. And what this does is it just makes it so that stack data is no longer executable, which then means that if we try to do a buffer overflow with shellcode that we write directly onto the stack, that's going to fail because that code that we wrote, we can no longer execute it. So what can we do instead? Well, if our own code isn't executable, how about we try using code that's already in the program, right? So the idea is maybe we can try to manipulate the code that already exists in some way that will allow us to arbitrate and or execute any arbitrary instruction that we want. And this might seem unlikely at first, like why would there just be malicious code sitting in a program? But x86 provides us a mechanism to essentially create this code from the pre-existing binaries. So x86 has variable length instructions. And what that means is because instructions are different lengths, there's no fixed offset from which you have to start reading a given instruction. And what that results in is the same set of bytes being able to be interpreted differently depending on where we start reading from. So you can see in this example right here, if we start reading from here, the instructions we get are increment EBP and return. But if we start reading just one byte to the left, it becomes increment RBP and then return afterwards. And so using this behavior, statistically in large programs, or programs in particular that contain large libraries like maybe standard IO, statistically we end up being able to find essentially any instruction that we could want. And so making use of this vulnerability, we can do something called ROP chaining, and ROP stands for return-oriented programming. The idea behind this is that even with this mechanism that we just discussed, it's a bit unlikely to find an entire block of malicious code just sitting in the binaries, right? Like there's no way an entire block of the code that you're looking for would just be sitting there, or maybe you're just really lucky. And so what we can do instead is break that code into smaller gadgets that will maybe do like one or two instructions and have all of those gadgets end in a return. So we can do this thing where we chain them together. And how this would essentially work is you would have the program jump to one gadget. It would maybe execute a couple instructions you can see like right here, and then it returns. And then what we put on the stack right after that gadget is the address of the next gadget. So if we put the address of this onto the stack, after we return from here, we could jump to here and start doing this behavior afterwards. So you can see by doing this, we can essentially chain together a bunch of smaller blocks of code to reconstruct a big block of code that wasn't originally part of the program at all. And so we can use this to essentially create any malicious code that we want. So as an example of how to use this, let's try to break into this checker function that we've defined right here. And in terms of problems, you'll probably encounter in exams and other problems in this course. Usually you'll have some kind of function you want to break by passing it a malicious set of arguments. In this case, we want to get past this check right here with the admin, the password, or the password length. An important thing to keep in mind with what the actual goal of the gadgets that we're looking for is that because x86 passes arguments by register, the gadgets that we're looking for should pop the values that we want into the respective registers before we perform this function call. And in x86 specifically, the order that they're going to be passed in is RDI, RSI, and RDX, which will correspond to these three arguments that we have here. So let's get started right away. We can see that we have a lot of relevant information that's been provided, a list of gadgets that we need, as well as some addresses that should be relevant. First of all, let's try to get the correct value into pass. And we can see that what this check is doing is it's comparing pass to the string who am I. So ideally we want who am I to be stored in our first register, RDI. But there is a bit of a nuance when it comes to strings specifically. When you pass in a string as an argument, it's not actually passing all of the characters on from the register in the argument, right? What it does, it might help to see here, it's a character pointer, and what it passes in is actually just a pointer to the first character in the array. So we just have to keep that in mind. We're passing in an address and not the actual string. Now that brings to mind, where can we get an address that contains the string from memory? This might seem a bit difficult at first, like where could we just expect some arbitrary location to contain the sequence of 7 characters? But recall, we have a buffer where we can write whatever we want to it. And DEP won't prevent us from doing this in this case because we're not trying to execute who am I, right? We're just trying to read that value and pop it off into a buffer. So what we can do is we want to use that value so we can write that into the buffer. So we'll write who am I there into the buffer. So we'll start by writing who am I to the buffer, and then let's add in the appropriate padding to get us to the return address, right? I'm going to abstract some of this process away because it should be familiar from previous slides. But yeah, let's just add in the padding to get to the return address. And the next step we're looking for is some gadget that will allow us to pop into that correct register, right? So we want to get into RDI, and immediately I see a promising candidate. We have this pop RDI and then a return, but it does seem a bit unfortunate that we have another pop RBX right before that. But as it turns out, that's actually not a problem, because if we want to get past this into the pop RDI, all we have to do is just put a garbage value to get popped into here before we put the value that we want to have into RDI. We could have like garbage, and then recall the value that we want. Oh, sorry. Before we do that, of course, we have to have the address of the gadget that we're jumping to as the return address, and then we fill in the garbage for RBX. And finally, we can put in the address we want to put into RDI, the start of that string, who am I, which is just going to be the start of our buffer. So let's just put that in here. And we can see now what we've done here is, like I said, we write the string, fill in the rest of the buffer, override the stored RBP, and now we're at the return address. So we want to return to this gadget right here. Sorry, I didn't mean to strike through that. But once we're doing that gadget, you can see that we're going to pop this value into RBX, just some arbitrary garbage, and then the pop RDI will take this value, the start of our buffer, and get that into RDI. Great. Now we've taken care of that. Let's try to get the second value that we need into the RSI register, which is where our second argument is going to be. You can see that our second argument now is going to be password length, and that's what's going to be passed into the string comp to tell us how many characters we should compare. Because we wrote just who am I, like technically I guess you could have written just like the W or WH or something like that, but because we wrote here 7 characters, that is the value that we're going to want to pass into password length. So we know that we want to pass 7 to here. And so let's just look for a gadget that will allow us to pop into that register. And actually, I mean, the one I underlined before, we can see it does exactly that. It's going to do this move instruction first. That's not an issue because it doesn't deal with the stack at all, and it doesn't mess with any registers that we were using. So this is fine. Then we pop into RSI, but you can see we have another like extraneous pop instruction, but we'll just account for that by putting in another garbage value. And like we always want with the ROP chains, we can see it does end in that red. So it's providing us exactly what we need. So all we have to add now is the address of the next gadget we want to jump to, the cafe, 0xcafe. Let's pass in that hex 7, and then some garbage once again. You can see what we're going to do here is it's going to pop 7 into RSI, right? So 7 to RSI, and then the garbage value is going to go into R9, and then we'll reach that return just like we wanted. So after we return from that first gadget that we put in with the C0DE, it's going to see this address, CAFE, and then jump to that next gadget. All right, great. And now we're almost there. You can see we only have one more argument we need to pass in. That's going to be the isAdmin value. And if we recall, that's going to correspond to the RDX register for our third argument. And so once again, let's perform this process of searching for a gadget that's going to do the behavior that we want. Right off the bat, I can see this one has a pop RDX and a ret, but we have to be really careful here, right? If we look at what other instructions are happening in this gadget, you can see there's a push RCX. So what this is going to do is push the value from the register RCX, then pop that value into RDX, and then return. So we don't really have any control here over what value gets popped into RDX, since it's just going to depend on what was in RCX in the first place. So this is a no-go. We can't use this one. Let's keep looking. Oh, fortunately, we see another one right here. This one's going to pop RDX and then return. And we can see it's just an XOR instruction right before that, so that doesn't have any issues. So let's go ahead and jump to that gadget now, 0xFADE. And then pass in the value we want, which is just going to be a 1. And now, after we return from here, we actually don't need any more gadgets, right? We filled in all the registers that we need to get past this check. So now we can just return to the checker function itself. So now we pass in the checker address, and yeah, that's it. So if we follow the flow of what we did, we wrote the string that we needed for the password, filled in the appropriate padding, returned to that first gadget to do this behavior right here, pop into RDI. And once we return from that, we pop into RSI using the gadget up here, and our final gadget will pop into RDX. And once all that is done, we can return to the checker function, and there we go, we're done. So hopefully this video was informative, and I hope you learned a lot about ROP chaining. Yeah, thanks for watching.